This is Mr. Anderson for Kellogg Community College. We are going to be looking at part 3 of our video on Chapter 2, Section 5. Going to be looking at some graphs here of secant and cosecant. We're going to do problems 5 through 8 on my worksheet here. Okay, so first of all, cosecant, let's mark out our asymptote lines, making sure my pen's turned on. Okay, so my asymptote lines for cosecant they're going to be every pi units. So this is going to be our 2 pi here in the middle. This is going to be pi, 2 pi, 3 pi, 4 pi, showing our 2 cycles here. This is going to also turn at every pi over 2 units. And what we're writing right now is we're writing the cosecant of x graph, which is going to turn at these 4 locations here where your x is 1 or your y is 1 and negative 1. Okay, now what I'm going to do here is I'm going to apply the amplitude of 1/2, which I can do over here on the right hand side. Again, I'm going to have the graph look the same, but let the points do the talking. I'm going to plot 5 points, and really I can count one of these asymptote lines as one of those points there, since I can only actually get 4 points on this graph very easily. So this is the location. If this was over here at pi over 2, then it's going to be the same over here. This is pi over 2 comma 1/2. This is going to be down here at 3 pi over 2, comma negative 1/2. And then this dot over here would be 5 pi over 2, comma 1/2. And this would be 7 pi over 2, comma negative 1/2. But let's get a couple of these asymptote lines in here to fill this in. This is the asymptote line x equals pi. This is going to be the asymptote line x equals 2 pi, and let's make this our 5th location here. This is 5 pi over 2, comma 1/2. All right, so we're going to talk about domain and range. Our domain are going to be all the x values except where the asymptote lines are at. So the domain is going to be the set of x where x cannot be equal to k pi, where k is an integer. I shouldn't have a comma there. The comma should go here, where k is an integer. And from the previous video, we talked about the integers being positive or negative whole numbers, including 0. So you would see that every single integer here would give you a interval of pi where the asymptote lines would be. The range is going to be where we would go from negative infinity to positive infinity on our x or y values here, and I wrote that with an interval notation instead of the r for all real numbers. So now what we're going to do is pretty much the same thing for our secant function here. Our secant starts at 1, just like cosine does, which is kind of neat because that is the reciprocal function of that. And the asymptote lines are at every pi over 2. So at every pi over 2, we have every pi plus our pi over 2 is going to give us an asymptote line. So this is 3 pi over 2, this is going to be 5 pi over 2, and 7 pi over 2. And then we have our points here for each of our graphs at 1 and negative 1 on every unit of pi. Pi, 2 pi, 3 pi, 4 pi. So here's pi, here's 2 pi, here's 3 pi, and here's that little half part here that rounds out at exactly 4 pi. Now see, this was our parent function of y equals secant x. Now if we go to the change of our amplitude here, then the graph is going to look exactly the same, but the points are going to do the talking, where we're going to go with 4 and negative 4. The asymptote lines will stay exactly in the same position because they are we're just applying right now an amplitude change. So this goes starts at negative 4 right there. So the graph looks the same, but it does get inverted like this because of the negative in front of the 4. So this is the point 0, comma, negative 4. There's our first of 5 points. let's put in our asymptote line right there. X is equal to, this is going to be pi over 2. Then we're going to have a line that swoops like this, and this is going to be the point at pi comma 4. Then we have another asymptote line here at y is equal to 3 pi over 2. And then what we'll have here is a swoop that goes like so. And that swoop is at 2 pi comma negative 4. So we got 1, 2, 3, 4, 5 points. We can keep going here. We can label asymptote lines and label points, but I'm going to count my asymptote lines as part of the points that I can use. But I am going to show all of my 2 cycles here by stopping right there, way over here at 4 pi comma negative 4. Now, in terms of our domain, this should be a little interesting here, because we're going to have to figure out a way to write the fact that this is an asymptote line at pi over 2, and then at 3 pi over 2, then at 5 pi over 2, then at 7 pi over 2. So x is not going to be at k pi over 2, comma, where k is an odd integer. Now, if you think about it that way, it's like 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. All of those odd integers, including negatives, negative 1 pi over 2, negative 3 pi over 2, negative 5 pi over 2, those are all not in our domain, and our range is going to be all real numbers. Because we're going to have, well, actually, whoops, holy moly, I can't believe I messed that up here. Oh man, I'm going to have to put an annotation in there, because in this case our ranges are not going to be all real, because our y values don't actually cross the spot of our integers, right, or our intervals right there. You'll notice that there's this dead space between the bottom and top of our dots there. So our range for these problems are actually not all real. So I'll put a little interval in there and just tell you guys that no, it's not the case. Our range for our secants and cosecants are going to be basically where y is below this ending part. So that y is below and equal to, because it has to actually touch that value at negative 1/2, or y is going to be greater than or equal to positive 1/2. So you'll notice that there's this chasm in the problem, but you'll notice that that can't be included in the range. As I originally said, it was all real numbers, because for a moment there I had a mistake thinking of tangent and cotangent, because that's what I did in the previous video. But of course, in these videos here, I got to make that little annotation that this gap between the 4 and the negative 4 is a gap in my range. So y is going to have to be less than or equal to negative 4, or y is greater than or equal to positive 4, and nothing in between. You can't write that like an AND function. It won't be good math grammar there. So again, sorry about that little mistake there. I'll try not to make that mistake in the next 2 problems. All right, so let's do problems 7 and 8, and then we'll call it square for this worksheet here, for this part 3 of 4-part video. So we're going to start off with the cosecant. And the cosecant has asymptote lines at every pi unit. So, and then we'll just quickly draw our picture here. Again, this nice to draw just the cosecant of x function, just so we can see that in there, and this is going to be a 1 and negative 1. So what we'll do is now change that, because we're going to make it half its height. So this is going to be 1/2, and this is going to be negative 1/2. And again, let's draw our little asymptote lines in here, every pi units. So again, we're going to have a swoop, but in this case, it will swoop at the positive and negative 1/2. Now, to add a little bit of work to this problem here, we're now going to change this cycle. We're actually speeding this up, so this is going to go in 2 cycles in half the distance, since we're speeding this up twice as fast. Now what I need here is a nice dot, and that dot is going to allow me to mark my point because this is going to be at pi over 2 comma 1/2. Now what I'm going to do is apply my omega for this problem over here on the next side. So this is a graph of 1/2 cosecant x. And now what I'm going to do is apply that omega of 2. So the omega is 2. So what I'm going to do is take my 1/2, which is my x value there, pi over 2, that one, and divide by my 2. Now, dividing by 2 is the same thing as multiplying by 1/2. So every single interval of this graph isn't going to be 1/2 anymore. It's going to be 1/4, or pi over 4. So this is going to be pi over 4, and this right now, this asymptote line, which used to be at pi, is now pi over 2. This is going to be 2 pi over 2, so this is going to be x equals pi here instead of 2 pi, and this is 3 pi over 2, and this is going to be x is equal to 2 pi. So what's happened is that this graph is going to complete its cycle in half the space it needed because it was twice as fast. The omega of 2 got us there in half the time because we're double the speed. So this would be the example of a note increasing in height for pitch, like it's a higher pitched note. So this is going to be 1/2, this is going to be negative 1/2. We'll use that as the 1 there, that little tick mark. So this means that this point right here, if I'm going to get my 5 pretty points, this is going to be pi over 4 comma 1/2. So there's my first point. My second point is the asymptote. It's not really a point, but it's the asymptote line, x equals pi over 2. This, since this is 1/4, this is 2/4, this is 3 pi over 4 comma negative 1/2. This would be 4 pi over 4, which is pi as the asymptote line. And this right here would be 5 pi over 4 comma positive 1/2. So there we go. And then we have 6 pi over 4, or this reduces to 3 pi over 2, 7 pi over 4 comma negative 1/2, and then we get to the 2 pi, which is going to help me when I get my domain and range. So let's do our domain. Our domain is going to be the set of x, and it looks like my, just like, you know, 2 problems, actually since we got to actually manipulate this as every pi over 2, so 1. So just like the problem above it, since we need an asymptote line at pi over 2, and then an asymptote line at pi, and then pi over 2, it looks like we're going to have where x is not equal to k pi over 2, where k is an integer. Now, that was a little different than the problem right above it, but it had some similarities because of the formula. But in this case, k, if it's an integer, it'll work for the even and odd pi over 2s, which gives us 1 here, because that's 2 pi over 2, 3 pi over 2, 4 pi over 2, which is all simplifiable to this, and 0 pi over 2. Now let's go do the range and not make a mistake and think it's all real numbers like I did before. This has a gap between the 1/2 and the negative 1/2, so y is going to be less than negative 1/2, or less than or equal to, sorry, and y is greater than or equal to positive 1/2, because it turns at that 1/2 moment. All right, so our last problem for this worksheet here is going to be looking at this problem, where we're going to start off with our secant. Now our secant starts here at 1, just like our cosine does. And so it turns, and it also has an asymptote line at pi every pi over 2, with an interval of pi there between these. So this turns here at pi and negative 1, 2 pi, positive 1, 3 pi, negative 1, and ends there at 4 pi, comma 1. Now we'll apply the negative 3 as our amplitude of 3 in the problem. Whoops, let me make that a positive 3 there. All right, so what this will do is it'll keep the asymptote lines in the same place. Keeping the asymptote lines in the same place, but what it will do, it will change the starting position of these dots. Like this is going to start down low instead of up high, like so, at the point 0, comma 3. Negative 3, excuse me. Our asymptote line is still y, or x equals pi over 2. So I'll put that in there. And everything else flip-flops. This is going to be pi and 3. This is going to be 2 pi and negative 3. 3 pi and 3 up again. And then down here, this arc is going to end at 4 pi, comma, negative 3. All right, so we're moving on to this problem here, which is going to be 3 and negative 3. We've got to work with this cycle change right here. So our omega in this problem is pi over 2. So I'm going to take my first tick mark, which happens to be the asymptote line. This asymptote line here at pi over 2, I'm going to divide that by my omega, which really is going to flip and multiply. So that what's going to happen here is I get a problem that's 1 over 1, which is just 1. So what's cool here is that this changes to integers like 1, 2, 3, 4, 5, 6, 7. So all of my asymptote lines are at these odd integers. X equals 3, x equals 5, x equals 7. All right, so what we have here is whoop. We have, oh shoot, I was copying the wrong picture there. We have whoop and then swoop. These swoops right here, we're going to swoop right there. This is the point 0, comma, negative 3. This is the point here. This is the asymptote x equals 1. This here in the middle is kind of fun because it is going to be, you know, since we've changed this to like numbers here, this is going to be 2, comma, 3. And then this is going to be x equals 3, and this is going to be 4, comma, negative 3. This is x equals 5, and then 5, comma, 3, x equals 7, and then 8, comma, negative 3 for this dot right down there. So what about my domain and range? Well, my domain, x can be anything except x cannot be any k where k is an odd integer. And what's kind of neat about that, you see it's 1, 3, 5, 7. So x cannot be an odd integer. You can also write it without the k there if you need to. X is not an odd integer. And for my range, again, not making a mistake, we are looking at the gap between 3 and negative 3. So y is going to be less than or equal to negative 3, or y is going to be greater than or equal to 3. There we go. Well, thank you for watching these graphs, and we're going to finish up with part 4 here, dealing with multiple movements and changes of these graphs with cotangent and cosecant, cotangent and secant. Thank you.